So let's see. You already are familiar with the format. So let me ask you, what was your concours ranking?
I guess I was among the lucky ones. I didn't have to take one.
You didn't have to take. Why? Were you an Olympiad person?
Yes, physics Olympiad.
Physics Olympiad. Where did you go and what did you get?
Went to Poland.
Poland.
Yeah.
And what medal did you get?
Bronze.
A bronze one. Okay. But still you didn't have to do that. Excellent. Ramin Farjadrad, the list goes on. Stanford PhD, go Stanford. Worked at Rambus and Sun Microsystems. I worked at Sun at the time you were over there. Co-founder and CTO of Aquentia for almost 15 years. Chairman of the Technical Committee NAV Alliance, Networking in Autonomous Vehicles for 4 years. CTO VP at Marvell, working on connectivity solutions. And founder and CEO of Eliyan Corporation, accelerating a smarter future by revolutionizing chiplet-based systems. Did it cover everything, almost everything that you did? Well, there could
almost,
be.
Yeah.
You went to Sharif.
That's right.
What made you come to the United States? Why did you leave Iran?
Actually, the main reason was back then in Iran, I wanted to pursue electronics, IC chips. And in fact, the first thing I thought I'm going to go do when I come here was doing an AI chips. This was way back then. And those basically technologies were not available in Iran. So it kind of...
Especially chip making to support AI chips.
Yes,
Who did you work with at Stanford?
Mark Horvitz and Thomas Lee. Yeah.
Okay. And after that, or during your studies at Stanford, you worked at Sun. Is that right? You were...
Correct, yeah.
And then you founded Aquentia.
Actually, Velio was the first company.
Velio was the first company before that. Okay, what did you do at Aquentia? What was the core of your activities over there?
So actually it started Aquentia, but the main focus was Ethernet PHY technologies.
Okay.
So back then I remember 1 gig Ethernet was around and people wanted to go to 10 gig. And there were maybe around 6 companies at the time working on this technology, and everybody said the power was really high because these PHYs were super complex. They were like 20 watts or something. And at these power numbers, they couldn't be basically deployed widely. So I guess we were kind of arrogant and felt that, hey, we can do better. So pretty much maybe 5 years after maybe the first companies started, we started in that field. And good thing in a couple of years we could catch up and do something that was better than others. And most of the companies went away except one big company. Broadcom was our big competitor, and for many years we had challenges.
But so arrogance worked there. So at some point you have to be confident about what you're doing, and it may appear as arrogance.
You can say that, yeah. But if I do it again, I wouldn't do that.
Oh, okay. Why? You're not a risk taker as much a risk as you took when you were younger.
No. Taking actually, I would take more risk than
you would
investing.
take more risk, okay.
Because back then we thought this is established market. We're gonna go, and Ethernet technology was something that made Broadcom, or Marvell technology. They all became tens of billions of dollars, and we thought we were gonna be the third one of doing the third generation of that technology. But we had a big challenge, meaning we had to. By that time, Broadcom was big enough. And they could, although we were always better, but there was something called like bundling. Like when a big company offered their products, they say, okay, I won't give you just this piece, but I'll give you tons of other pieces, and you have to buy the whole thing from me, rather than just pick the best parts. This is called bundling. That was become basically...
They did a Microsoft on you, essentially.
Pretty much, you can say that. And for some reason they could do it,
Yeah.
Nobody tried to break their
until they become sued.
Monopoly there. And that was one of our biggest challenges, which was the first product. And as a result, we decided to take maybe more risk, meaning figure out we don't want to compete with them continuously on this front, and pick a field that nobody was paying attention, and started doing a technology on that front. And
Which field was it?
this was what we call the enterprise Ethernet. Pretty much since early 2000, all the enterprises were being routed with 1 gig cables or Cat5 cables, like these blue cables you see on the top.
Right.
And they're capable of like up to 1 gig. And with technology demand and bandwidth demand, like wireless went beyond 1 gig to 2 gig, 5 gig, 10 gig. But these cables with existing technology couldn't go there. And the notion that everybody was, well, if you want to go to the next level, you have to change all cabling.
Yes.
Like thousands of cables within the solution or these buildings. So the idea we had, like, come up with a solution, a technology that can actually push, 2, 5, 10 gig into these cables. So that was something that we created from scratch and turned into standard, and actually pretty much all the Wi-Fi access points you see here right now has our chip right now.
Excellent. Marvell's acquisition of Aquentia in 2019 marked a significant milestone in your career. Could you describe the transition and your role as CTO, VP of Networking and Automotive physical layer at Marvell, especially in the driving the architecture for autonomous Ethernet physical layer up to 50 gigabit per second or per lane? That's what you did at Marvell. But your role changed, right?
Pretty much you can say yes and no in different ways. Like back in Aquentia, in fact, the automotive technology we started at Aquentia. And that was, they call like cars are servers on wheels, and especially the autonomous cars. The big need was how to connect all the pieces, not, the processors, GPUs. There are tons of sensors. There's like, they call it sensor fusions all around the car, not just cameras, but LiDAR, radars, and so on and so forth, that this whole thing has to be connected together efficiently and very reliably. And a key part of it was how to do it, especially in spite of, the car can have, get a lightning, and still the links have to all work and so forth. So that was the kind of technology we started. That was another new kind of solution that we started back then.
In Aquentia?
At Aquentia,
yeah, Aquentia.
And this nav that you mentioned was part of this, because usually when you start a new technology, you need to have support and alliances from the industry. If you just build something and say, hey, here it is, so good, it's not going to work. So we started building alliances with car companies, whether it's Volkswagen, Porsche, BMW.
That was the NAV alliance.
NAV alliance,
yes. You're anticipating my next question, but that's okay.
Because it all kind of ties into...
But let me ask you, did Marvell have similar technology, or by acquiring you, they were able to go into that area of the technology?
Marvell was the leader in the low-speed technology. In fact, the 1 gig technology that they had. In fact, we had a lot of challenges, especially with the Marvell team, as well as making our solution, which was 10 gig to all the way 100 gig, make it a standard.
So in going to Marvell, you not only had to deal with some technical issues, there were some political issues, because they already had some people working on a similar issue.
Very much,
okay,
yes.
I see. Okay, that was the question actually. How did you manage the politics and going into that?
I would say it was very difficult. That was my first role as an executive in a public company, which had thousands of people, and realized that I wasn't built for that necessarily. It was like somebody who'd been skiing all his life, and after 20 years, they say, okay, take off these skis, put on a snowboard, going down the hill, and I kept falling.
I see. So that was your motivation to go and found Eliyan.
Exactly, yes.
Okay, but before we get to that, you were the chairman of the technical committee of NAV Alliance, which is Networking and Autonomous Vehicles. What were the main objectives of the alliance, and how did your leadership contribute to advancing networking technologies in autonomous network vehicle? You answered part of the questions by saying, the requirement, but tell us, tell to the audience, why is this so important to have 50 gigabit per second on a car?
So this all comes back to the fact that, you know, once, especially you're on like level 4 or eventually level 5 autonomous car, that
Level 5 of fully autonomous.
fully autonomous,
Yes.
right? But even at level 4, you need.
What is level 4? What's the difference between, you know, for people who may not know, level 4 and level 4? Level 3 we already have, and Teslas are already level 3.
So level 4 kind of says hands on off wheels, right? But you just need to have your eyes on the road. That's the kind of thing that it is. Level 5 is that
Completely. You
eyes
can
on
go
the road. You
to
can
the
go
back and make a sandwich. And
exactly,
yeah.
right. So when it gets to those levels, you can say, yes, human beings, you know, they just have 2 eyes and 1 brain and, you know, function it all together. But for a car company, if they have an accident, you know, except if you're Tesla, but any other car company, you have an accident, you get into serious trouble. So especially the German and you know, Japanese car companies, they wanted to make sure that there is 0 chance, like 1 in a billion chance of accident. So for that to happen, you have to, as I said, tons of sensors around the car that are tightly connected to each other with a lot of redundancies and so on and so forth. So in fact, Ethernet was one of those networks that provided a lot of these resiliency to problems. If a part of a network crashes or has an breakdown,
yeah, it works.
Still there are other ways to loop back and, you know, connect everything, still keep everything connected together. So that was kind of the basis of it, because before that people didn't have necessarily a network in the car. There was just like certain wires connecting point to point. And we wanted to push Ethernet into the car. And to do that, every time you want to take a new notion, a new concept that people are not comfortable with, you have to start talking to them one-on-one, explain to them, get them comfortable, and basically bring them to your turf, and then go and present it to the world. So
a lot of politics.
Yes.
Okay.
Nav Alliance's role was pretty much that, to talk to each one of them separately and bring them on board.
You were the leader there, the chairman, for almost 4 years.
That's right.
So we suppose you succeeded in doing that.
Yeah, eventually basically 2 technologies turned into IEEE standard.
Excellent, excellent.
Yeah.
You are currently the founder and CEO of Eliyan Corporation, and you are focused on revolutionizing chiplet-based systems. First of all, explain to us, to the rest of the people, what is a chiplet-based system? It helps with the yield. That's the old purpose of it. But I'm sure it does other things that is more useful for your mission of your company.
Sure. So I'm sure everybody has heard about Moore's Law. Moore's Law, or maybe haven't.
Moore's Law. Oh, no, I misheard this. Moore's Law. Yes, I have
Moore's
heard
Law,
about
which I think maybe about 40-some years ago predicted that every
Gordon Moore, the founder of
Intel.
Fairchild, who later on founded Intel.
Intel,
Yes.
exactly, yes.
He said what?
That basically every 2 years, the density of the gates or transistor per area will double in a chip. And as a result,
Nitpicking 1.5 years, but that's okay, yeah.
Or 1.5 years, there you go. And this actually was a very accurate prediction.
Yes.
And there's a lot of reasons behind it. That and performance, maybe, I don't know which cause was, which one was the cause, which one was the effect, but the performance demand for compute was also similar. Every 1.5 to 2 years, people wanted something that was twice as fast. But 2 things happened. First of all, the transistor levels got too closer to the angstrom level, that it was really difficult to build transistors smaller and smaller. And at the same time, AI happened, that like started skyrocketing the demand for high performance.
Yeah.
So people, rather than fitting as many processing power within a certain chip or size, they started growing the chip to the level that the chip couldn't be built any bigger. Like NVIDIA chips, for example, GPU are at the maximum chip size. That
because of the yield problem, essentially. Once you make it very big, something goes wrong with it.
Even NVIDIA right now is building the biggest chip possible.
Okay.
So they have other ways with redundancy and so forth. They deal with the
within the chip, yeah.
Within the chip.
Rewire them, yeah, essentially.
Going beyond that is not possible.
Yes.
But one way to actually extend that size is to basically tile these chips together and build bigger and bigger chips. So it's not limited by the reticle size of this, semiconductor chip and so forth. So that's one angle of it. The Moore's Law, or kind of addressing the Moore's Law in one way. But the other challenge is Moore's law has been a great way, or basically, to get significant performance out of the chips. In the last 20 years, the performance of a processor or GPU has gone up by 100,000x, effectively.
Yes.
But at the end, a processor needs to process data. The data usually sits in a memory, and this memory has been sitting somewhere off chip, in some other chip in another, connectors and so forth. And the bandwidth bottleneck between the processor chip and so forth has been really limiting this bandwidth. This bandwidth has gone up maybe 30x, 50x in that range, while the other one has gone up by 100,000. So there is more a gap of maybe 1,000x between what the processor can process versus the bandwidth to the memory.
So you can calculate it, but you cannot quickly send it back and forth to see that.
So
okay, so how does the chiplet system help with this? Because you pick and choose, or how do you increase the communication between the chips?
Pretty much chiplet system says remove or eliminate anything that sits in between the chips, whether it's a package, it's a connector or whatever, put all of them all inside one package, as if they're all sitting on the same chip. The
and
memory
do you pick and choose, or you broadcast to all of them, or?
No, you just eliminate the bandwidth bottleneck between them.
So that would help the bandwidth problem, essentially.
Yes.
And you've done that. How do you see the role of chiplet-based systems evolving in a broader landscape of technology and semiconductor development? It's not going to be only used for the cars.
No, not only used for the cars. In fact, the biggest use for it right now is generative AI. Actually, or AI and then generative AI. The main chips that are built with chiplets, whether it's NVIDIA, AMD, Intel, or all those chips, they have to use chiplets to address the high-power AI requirements.
Okay, so these are chips like, again, as was mentioned, H100. Do they use this technology? They are using it right now?
They are using it right now,
okay.
Yes.
So what is Eliyan's contribution? What is your goal what to add to this one?
So to build this chiplet or chiplet system, there's a special type of packaging. They call it advanced packaging because it's advanced and complex. And right now, very few companies have access to it, like NVIDIA's or AMD's or Intel, the big, really big companies. And they've, in fact, got a hold on the market on these solutions right
So
now.
this packaging involves 3D, a special
3D,
communication. So that is a hardware-intensive method in order to win the next battle of semiconductor.
Exactly. Yeah.
I see. And you have some ideas how to win through Eliyan.
So we say rather than finding basically a manufacturing way to connect these chiplets together, we give you an electronic way to connect these chiplets together without any of these advanced solutions. So basically democratizing the use of chiplets for everybody. So people don't have to resort to, let's say, for example, TSMC, that is currently the main supplier, only supplier of this solution, to basically be able to get that, while the 2-3 big companies that basically have a hold on those.
What's the trade-off? You democratize it, you make it simple, you make it through electronics, but not through fancy configuration or 3D. What do you give?
So there's hardly any negative.
There's no negative.
In that sense, but tons of positive. Even companies like NVIDIA's and so forth can benefit from our solution, because advanced packaging, for the same reason that is advanced and complex, once you start making it larger and larger, the yield drops and challenges comes in.
Yes.
But if you don't use it, then they can build a very large systems.
Excellent.
All inside a single package. So their performance actually can go up by 5x, 10x, 20x as a result.
How big is the company now? How many people?
We are about 50 people.
50. And I don't know if there are any hardware people. Are you hiring?
Sure. Yeah.
Okay, people know where to go to after this. I would like to leave some time for questions, and we have a hand raised over there. Can we get a microphone over there, please? It's a long way, so.
Thank you very much.
Please state your name and affiliation. I forgot.
My name is Ehsan Soudi. I'm an engineer at Infinera Corporation. So with regards to the bottleneck of the chip-to-chip communication that you mentioned, how would you see the optical interconnect solution and your technology, actually, with your company, how does it compare with? Because NVIDIA and Intel, as you know, they are also investing in that technology to have basically replace copper with optical. Yeah,
So,
thanks.
yeah, very good question. So right now our focus is mainly inside the package or like intra-package. And our solution is complementary to the optical. Optical, usually when you want to go several meters and connect a larger system together, you go optical. And that's kind of replacement for the way that copper has been, or the solutions that copper has been providing. But then still, to be able to build more higher performance or more effective heterogeneous systems, you need to go chiplet route, meaning you have to have your silicon photonics in a special process, like an SY process, connecting to like a FinFET process in 3 nanometer. So to connect these two efficiently, you either have to go advanced packaging or use our technology. So the two are very complementary.
Any other question? We have time for one last question, Babak.
Hi,
No, wait, it's over there. Sorry. Okay.
this
You
is
have a question? Yes. Okay. Maybe. Go ahead.
Rishikesh here. I've worked with Samsung, Toshiba, and others. Is your technology compatible with UCIe?
It is also compatible with UCIe, yes.
Is
In
it
fact,
a different flavor of it? Can you go a little bit detailed there?
so this technology is, we did a lot of new technologies at Aquantia, my last company, but it started at Aquantia for yield reasons, that we started a chiplet connectivity solution. And because it was super efficient, it was adopted as a standard at Open Compute Platform back in 2018, 19. And then UCME came along and uses very similar, fundamentally same signaling system and so forth. So as a result, our solution is fully compatible with both. So basically, we have it configurable to support both scenarios.
And the last question comes from Babak.
Thanks for the presentation, Babak from Juniper Networks. So chiplet is a really good idea, but at the same time, you have lots of interfaces that you create. Now, if you have this MCM module that wants to go to the car, you have reliability issues. No one has checked how those going to behave. Any comments on it? Is it going to pass AEC-Q 100, you know, reliability requirements and stuff like that?
Sure. Yeah, actually, that's a great question. So for advanced packaging, as you said, that most chiplets, high-end chiplets you're using, they're not yet qualified for the car, and there are a lot of discussion in industry how to manage these tiny microbombs, 10 micron microbombs or TSVs and so forth. Again, this is one of the key advantages that we have, that we avoid all those new manufacturing and stay with, from mechanical manufacturing point of view, stay with the old way that things are done. So some of our chips that are already being tested, you know, by car companies, they are like chiplet based, but based on this technology.
Well, thank you very much, Ramin Farjadrad. On behalf of, wait, I have to say my thanks, and then you can clap. On behalf of Plug and Play, Persian Tech Network, and the Iranian community in the Bay Area, I would like to thank you for accepting our invitation and coming over here. Thank you. Now it's the time. Thank you.